Hey there, have you ever thought about how drilling companies could know where to drill? How could people know what's underground even before they dig it up? What if I told you that there is a way? That there are people that can send waves through the ground, detect and understand its reflections, and identify deposits below the ground. Truth is, companies are already doing that, and it's called seismic imaging. Just that instead of humans, it is machines that are sending and reading the waves, and the human interprets the readings. Problem is that interpreting seismic images is really tedious. Imagine you're expected to look at tens of thousands of pictures that look like this. This is why we get our trusty friend, the computer, to help us. Unfortunately, it is not as simple as that. How can a computer know that there's salt in an image? This is where we use computer vision and machine learning to help us. Remember, your computer does not have eyes, so computer vision works by using the values of pixels in an image to detect certain patterns. In this case, our images are in grayscale, which means that a pixel intensity can fall anywhere from 0 to 255. 0 stands for black, and 255 stands for white. Because we are concerned with the issue of identifying the presence and location of salt in an image, we need to tell the computer where the salt is in the image. In computer lingo, we need to tell the computer the exact pixels where salt exists. What's next then? This is where machine learning comes in. There's a lot of hype about machine learning in the past few years, and it can get really confusing trying to figure out what exactly is machine learning. So let's use an analogy. Do you remember how you learned to read? I remember being exposed to alphabets and the pronunciations. Over time, I just learned how to pronounce each alphabet. But if you asked me what happened in my brain that facilitated the learning, I couldn't quite possibly tell you. This is the inspiration for a machine learning model called neural networks. Think of each node in the model as a neuron in the brain. When it sees a certain pattern, it will light up. When enough nodes light up, then you will probably see a representation of something, say an alphabet or a car. We use a special type of neural network called convolutional neural networks, or more commonly known as CNN. CNN works by applying a convolution operation to the input. Think of each convolution as trying to tell us a feature of an image. The shallow layers will tell us the more basic features like horizontal or vertical edges, and the deep layers will piece together these information to tell us if this picture contains salt, by examining how images with salt look like. There's a problem though. Typically, CNNs are used only for classification. It tells us the existence of some property in an image. However, for this problem, we also want to know the exact location of the salt, so that we do not waste the money and resources drilling in places where there is no salt. This is where our UNet model comes in. On top of identifying whether the image depicts salt, it also tries to predict where the salt deposits are by looking at lower level features, via deconvolutions. So, with the UNet model, we have the prediction for the pixel location of salt in an image. Of course, if the network predicts that there is no salt in the image, then no pixel location will be output. I'm sure you're curious. How does this model perform? This model can give around 85% accuracy. While it may not be perfect, you can think of how many man-hours machine learning has helped us to save. Also, it is important to note that even humans cannot generate 100% accuracy. Hence, it is fair to conclude that this method is working quite well. How would you pre-process each image so that better results can be obtained? Let us know.